Okay, so this problem is asking us to determine the spring constant for this block that's connected to a spring and pulled a distance of 20 centimeters. And it tells us the subsequent oscillations have a period of 0.8 seconds. So let's first write our givens and finds. So our givens, let's see, we're given that our mass is equal to 0.5 kilograms. Right, 500 grams is 0.5 kilograms, and our period, capital T, is equal to 0.8 seconds. And we have to find the spring constant, which is K, and we have to find the position or positions, so x's, when the speed for v equals 1 meter per second. Okay, so there's two ways that we can do this, right? So let's start with A if we're going to find the spring constant first. And we'll do A by way of the energy method. Okay, so if we want to do energy, we're going to use the equation E is equal to kinetic energy plus potential energy. And that's equal to kinetic is 1/2 mv squared from last semester, plus 1/2 kx squared. And this is coming right out of your book. So if my writing isn't that great, you can look in the book. Okay, and that's also equal to 1/2 k capital A squared. And why is that? So let's draw a picture first. So let's say we've got, let's say this is a wall. This is my spring. This is my block. And when it's not stretched or compressed, we're going to say that that position is the equilibrium position, and we're going to say that is x is equal to 0. So that's my x equals 0. And on this example, we pull the block 20 centimeters away. So we're going to draw, like let's say it's extended to here, right? And so this is 20 centimeters away. So it's just been pulled away. So the spring is stretched. So my amplitude now, if I were to draw this, my amplitude for position, the max it can be is it's going to go from 0 to 20. And then what's going to happen is the block is going to move from, let's see, it's going to start here, and then if I pull it, it's going to go to here. So it's going to start at 0, go to 20, and then if we let it go, it's going to go somewhere, let's make this red, somewhere like over here.
That wasn't the number.
So that's going to be 20 away. So that's a negative 20. So that's the max that it's going to be. So I'm going to have something that looks like it starts at 20, goes to negative 20, and comes back up to 20, and then keeps going, right? So it keeps going. So this is 20, and this is negative 20. Okay, and so that's my A, that peak from the origin to that peak of the cosine wave is A. So what does that mean? Well, I can think about the potential energy is 1/2 kx squared, and when it's fully stretched to 20, I can think about what is my x. Well, my x I know for a spring is the amplitude times cosine of omega t plus phi, right? And when it's fully stretched, then I know that my x is going to equal a. I know when it's fully stretched, I know this is going to be equal to 1. So I can represent like x max is equal to a. So when I can put that into my expression here, so when I'm fully stretched, my block isn't moving. And so what happens then is my kinetic energy goes to 0, So this term, oops, this term here goes to 0, and I just have 1/2 kx squared is equal to 1/2 ka squared. And I know that that's by conservation of energy, right? My maximum energy is going to be 1/2 ka squared. So I know if I'm either have all of my energy in potential energy, meaning I'm fully stretched, the spring is fully stretched or the spring is fully compressed, then I know that my maximum energy is going to be 1/2 ka squared. But I also know that when x is equal to 0 and there's the potential energy is 0, that my kinetic energy, 1/2 mv squared, is going to equal to the total energy, 1/2 ka squared. So, oops, let's just, okay, let's see if I can push this up. Okay, so what I can do then is I can say, okay, when I have all kinetic energy, so all kinetic, switch back, all kinetic, that means that I'm going to have 1/2 mv squared is going to equal 1/2 ka squared. Okay, so what do we know about v? Well, if we know that x of t is equal to a cosine omega t plus phi, then if we want to find the velocity is just the derivative of the position. So that's just going to be x dx of t dt. And when I take the derivative of x, I'm going to have a, the derivative of cosine is sine, and then I take the derivative of the argument. So the derivative of omega t is just omega. So that means that I have, I can plug that in. So I also want to think about this. If I know at that time when there's no potential energy that my kinetic energy is a maximum, which really means I have the velocity as a maximum. So V max is going to equal, I have A omega, those are my constants, and then I have the sine omega t, and sine omega t, well that, for V max, that has to equal 1. So really then my V max is just A omega. Let's see. Okay, so then I'm going to plug V max into this equation right here. So I'm going to say 1/2 m times A omega squared, right? I'm just plugging in V max there, is equal to 1/2 Ka squared. Okay, so a half is common on both sides, so I can cross them out. And I have A squared here, and I have A squared here. So I'm left with m omega squared times is equal to K. Okay, so I'm trying to find out what K is. So if K is equal to m omega, well, K is equal to mass is 0.5 kilograms. And what about omega? Well, omega, just do that over here, is equal to 2 pi over the period. And they told me that the period is equal to 0.8. So I'm going to put that in as a fraction. I'm going to say that's equal to 8 over 10. And then I'm going to rewrite that as omega is equal to 20. So I'm going to take that 10 and multiply times the 2 on top, 20 pi over 8. And when I simplify that, I can divide both the top and bottom by 4, and I get 5 over 2 times pi. So I can put that in here. So my omega squared is 5 over 2 pi, and square it. So my K, when I work all that out, is 30, it's 30.8, but I'm just going to say it's 31, and this is newtons per meter. Okay, so that's my one way to solve it with energy. And now I want to show you the same thing with force. So this problem's a little longer just so I can show you that you can do the same thing with both methods. So this is the force method. So I have, think about, I've got the sum of the forces is equal to ma because my block is moving. And so the only thing in the horizontal direction I'm thinking about is the spring. So I'm assuming that my surface is frictionless. So the only thing acting on my block is the spring. And so I know that there's a spring constant, kx. And for now, I'm not going to worry about the negative. I know I'm always pulling opposite to the direction of motion, but I'm not going to worry about it. I just am looking for the value of k. So I've got ma. Okay, so now I'm looking for k, and I have x and I have a, but I know that x is equal to x of t, terrible x of t is equal to a times cosine omega t plus phi. Right, so I know then v of t, I take the derivative, and I get a omega, just like we did earlier, a omega times sine of omega t plus phi. And now if I want to find the acceleration is just the derivative of the velocity. So that is a omega, and the derivative of sine is cosine. And then the derivative of the argument inside the sine is just omega. So then a of t is equal to omega squared a times cosine of omega t plus phi. And you'll notice that that's just x. So this piece right here is just x. So that means my a is equal to omega squared x. And I'm going to plug that back in right up here. So I'm going to have kx is equal to m omega squared x. So I can cancel out my x's. Let's do that with red. And I'm left with k is equal to the same answer, same result. K is equal to m omega squared, and when I plug in my numbers, I get k is equal to 31 Newton per meter. Okay, so that's our answer for part A. And now we're moving on, and part B, if we just rewind that and just take a look. In part B, we want to know what is the position or positions the block speed is 1 meter per second. So what we're going to do here is we're going to use the same equation again, the energy equation. So this is going to be B. Oops. B. And we're looking for the position given V is equal to 1 meter per second. So let's use the energy equation again. And just so you know, we don't have to use the energy equation. We could actually start with the position equation and figure out the velocity by taking the derivative and then plug in values to find t and then use t to plug back in for x. But we're going to use the energy this time. So we're going to say energy is 1/2 mv squared plus 1/2 kx squared is equal to 1/2 ka squared, the amplitude squared. So remember that's true because of conservation of energy. So what we're going to do now is we're going to let's see, where am I? Right. So here I'm going to say I've got just this right equation. So I'm going to get rid of all the 1/2. Oops. Get rid of my 1/2, and let's do this in red. And what I want to do is solve for x. So the thing I want to solve for here is x. And so to do that, I need to get x alone. So I'm going to subtract the 1/2, or the mv squared, and bring it over to the other side. So I have k x squared is equal to k a squared minus mv squared. And now I want to divide through by k. And I have x squared is equal to a squared minus m over k v squared. And so here I've got x squared is equal to, let's back up 1 second. So now we can say x is equal to the square root of a squared minus m over k v squared. And when we plug those numbers in, we're going to have x is equal to, a is 0.2 meters squared for 20 centimeters, minus mass is 0.5 kilograms, divided by k, which is 31 newtons per meter. Oops. Add a little 1 in there. And then v squared is just 1 meter squared. And that's all. I'll take the square root. And now when I go through and do the math, I find that x is equal to 15 centimeters. So 0.15 meters, but I'm going to write it as 15 centimeters. And that's our answer.